today I'm going to be, hey everyone, I am Mylon Aikman, and today I'm going to be showing you how to calculate all of the statistics for a one sample t-test by hand. Not totally by hand, we are going to be using a calculator to assist us with some of the math, but it's a very simple calculator. So here we go. I'm going to show you how I think about this, how I approach this. Let's get rolling. So when I'm trying to figure out how I should be doing something, the first thing that I do is I check the formula. The formula for t, for a one sample t-test, is t is equal to a sample mean minus a population mean over the standard error. And I look and I see what information I have. So here I have a bunch of x values. These are my scores. I've got 2, 1, 7, 3, and 4, and I have the population mean. So let's look at our formula. Do I have the sample mean yet? I do not, actually. I need to calculate the mean of all of these things. Do I have the population mean? Yeah, I do. If you're doing a one sample t-test, you presumably know the population mean or whatever it is you're using as the population mean. So you should always start with that information. And then finally, we have a standard error, which is not a number that we have yet. So our first things first, I'm going to go to this t-test formula and I'm going to say, okay, what's the first thing that I'm missing? First thing that I'm missing is the sample mean. So I'm going to calculate that. The formula for the sample mean is just the formula for a mean. It is going to be the sample mean is equal to the sum of all of the scores in your sample divided by the number of scores in your sample. Do I have the sum of all the scores yet? No, but we do have the scores, so we can calculate that. Do I know how many people I have in my sample yet, or how many scores I have in my sample? Well, let's look. I have scores for 1, 2, 3, 4, 5 people, or unit, whatever. I have 5 observations. So my sample size, n, is 5. This means that I have all the scores and I know my sample size, so I can calculate the mean of my sample. So to do that, the first thing that we're going to do is we need to get the sum of all the scores, the sum of x. So I'm going to take my scores and add them all together. 2 plus 1 is 3. 3 plus 7 is 10. 10 plus 3 is 13. And 13 plus 4 is 17. So the sum of x is 17. If I add together all the scores, the sum is 17. Then I divide it by how many scores I have. N is 5. So there's that. Our sample mean is going to be 17 divided by 5. So that's 17 divided by 5 equals 3.4. There's our sample mean. So my sample mean is 3.4. When you're doing these, I highly recommend you keep a list of all of the statistics that you've calculated as you're going, just so it's easier to find them. And in this case in particular, because I'm going to have to erase some stuff to, have room for what I'm doing. All right, so now we have the sample mean. We have this missing piece of the equation, and we have the population mean that was provided to us for the problem. We do not have the standard error, though. So how do we get the standard error? Well, I'm going to show you the standard error formula. The standard error formula for a one sample t-test is, there's 2 versions of it. We can either do the standard deviation of the sample over the square root of the sample size, or we can do the square root of the variance over the sample size. We can do either of those. So first things first, let's look. Do we have the information that we need to calculate the standard error? This version of the formula calls for the standard deviation, and this version of the formula calls for the variance. We do not have either of those, so we cannot use either of these formulas yet. At the bare minimum, we need the variance, or we can get the standard deviation. We need one of those two. But we at least have the denominator. We at least have the sample size, which is 5. So we need to figure out the standard deviation before we can calculate the standard error, which we need to calculate t. So how do we do that? Well, the formula for the standard deviation, I'm just going to go straight to the standard deviation. I'm going to use this version of the formula. The formula for the standard deviation is the square root of the sum of squares, which is the sum of each score minus the sample mean squared, divided by the degrees of freedom, which is your sample size minus 1. Now let's just this formula, see if we have enough information for it. Do we have our scores? Yes, we have all 5 of our scores. Do we have the sample mean? Yeah, we just calculated that. It's 3.4. And do we have the sample size? Yeah, we do. It's 5. So finally, we can do something. We have enough information to calculate our standard deviation. So I'm going to start that in a different color. The standard deviation is equal to the square root of x minus m squared. Do we have x minus m squared yet? No, we do not. So let's figure out this. Let's figure out this top equation. And this is going to be several steps. To do this, we've got to remember PEMDAS. Parentheses first, then exponents, then multiplying and dividing, then addition and subtraction. So first, let's do the bit in the parentheses. That means we're going to take each score, each x value, minus the sample mean. That is our first step. So first, we're going to take 2 and subtract the sample mean. 2 minus 3.4, that is negative 1.4. Then we do that for the next one. We're just going to do that all the way down. 1 minus 3.4 is negative 2.4. 7 minus 3.4 is, and this is me doubting my math again, 7 minus 3.4. If you're allowed to use a calculator, there's no shame in doing it. 3.6. Then 3 minus 3.4, I believe, should be negative 0.6, but I'm going to check because I'm bad at math. And like I said, there's no shame in using a calculator if you have one. Yep, that's negative 0.6. And finally, 4 minus 3.4. I'm going to do this again. 4 minus 3.4 should be 0.6, right? Yeah, 0.6. So that is the parentheses part of this equation. The next thing that we need to do is we need to square all of these. So I'm going to create another column and call it x minus m squared. Remember, PEMDAS is parentheses first. We just did the parentheses. Now we get to do the exponents. So what we're going to do is we're going to take each number here and square it. First, we have negative 1.4. And keep in mind that when you square a negative number, it's going to turn positive. So I'm just not going to put the negative when I put this in the calculator because it's not really worth the effort. I know I'm going to get a positive number. So 1.4 squared gives me 1.96. So negative 1.4 squared is 1.96. And then we do that all the way down. Negative 2.4 squared is 5.76. 3.6 squared is 12.96. 0.6 or negative 0.6 squared is 0.36. And positive 0.6 squared should also be 0.36, based on what we know about squaring negative and positive numbers. All right, so now we've done the exponent part of this equation. Next, the final bit of this, the numerator of this equation, the final bit of the sum of squares is we have to add all of those squared distances. That's why it's called the sum of squares. We're adding a bunch of squared numbers. So we need to add all these together. That's why it's called the sum of squares. It's the sum of a bunch of squared numbers. So I'm going to take this 1.96 plus 5.76 plus 12.96 plus 0.36 plus 0.36. And that's going to give me 21.4. So my sum of squares is going to be 21.4. And of course, I'm going to make a note of that here in case I need it later. There we go. So now we know the top of this equation, and we actually also have enough information to fill out the bottom. So let's keep going with this. S is equal to the square root of the sum of squares, which is 21.4, divided by, make that a bit taller, divided by our sample size, which is 5, minus 1. All right, let's simplify that down a bit. So that's going to be 21.4 divided by 5 minus 1, our degrees of freedom, is going to be 4. Now, the first thing that we're going to do is we're going to divide, because essentially we can treat this as if these are in parentheses within the square root. So we've got to do this first, then we can square root. So that's going to be 21.4 divided by 4. And that is going to get us the square root of 5.35. And now we can take that square root. So by the way, before we take the square root, this number, 5.35, this is our variance. So if we want our variance, if we wanted to do this version of the standard error equation, we would plug in 5.35. So I'm going to make a note of that just in case. But we're going to simplify this down all the way to the standard deviation. So to do that, we take this 5.35, and then we take the square root of our 5.35. And that's going to give us 2.31. I'm rounding to 2 decimals because that's APA style. 2.31, though, you know, various teachers will have different preferences on rounding. So our standard deviation is 2.31. Nice. We've figured out our standard deviation. So why did we do that? Well, it's because we needed our standard error. So let's check our formula for the standard error. We decided we were going to use the standard deviation one, which is the standard deviation over the square root of the sample size. And now that we have the standard deviation, we have enough information to calculate this. So let's do that. Let's calculate our standard error. The standard error is equal to the standard deviation, which we calculated as 2.31, divided by the square root of your sample size. Our sample size is 5. We have 5 scores here. There we go. So first, I'm going to take that square root of 5. So square root of 5 is about 2.34. We're going to take 2.31, divide that by 2.34, and that will get us our standard error. This is our estimate of sampling error, about how far off on average should our sample be from the population. And our estimate is 0.99, rounding to 2 decimal places. So there's our standard error of 0.99. Nice, now we have our standard error. So let's go back and let's look at our t-test formula. That is our sample mean, which we have, that's 3.4, minus the population mean, which is also something that we have that was given to us, it is 3, over the standard error, which is the thing that we just calculated, this 0.99. So now we can finally calculate our t-test. We finally have enough information to do that. So t is equal to our sample mean minus the population mean over the standard error. Our sample mean is 3.4. Minus the population mean, which is 3, divided by the standard error, which we calculated as 0.99. So first I'm going to do 3.4 minus 3. So 3.4 minus 3 is going to be 0.4. And then I need to divide that by 0.99. So that's 0.4 divided by 0.99. Our t-value is 0.40, rounding to 2 decimal places. There we go. T equals 0.40. Now, if you want to figure out whether this is significant, you're going to need to look up your critical t-value in the t-table using your degrees of freedom. Our degrees of freedom, so our sample size was 5 minus 1, our degrees of freedom is 4. So we'd go to the 4th row of the t-table. We'd probably be using alpha 0.05 two-tailed, and we'd look up our critical value. In this case, we don't actually really need to do that. So like the minimum possible critical value to reject the null, assuming that you have an infinite sample size, is 1.96. If your t-value is closer to 0 than plus or minus 1.96, you fail to reject the null. And this 0.4 is definitely closer to 0 than that barrier. So I think I can pretty firmly say that we failed to reject the null here on this t-test. But yeah, if you would have to use the t-table to figure out if you reject the null or not, if this was a bigger number. But there you go. That was calculating all of the statistics for a one-sample t-test by hand.